Hey everyone, my name is Akshay Dayal. I'm a software engineer at Google, and this talk is going to be about my team's experiences using and scaling Jenkins. We're part of the developer infrastructure group, and what we do is work on build and release services for other Googlers. We recently started working on a new service and decided to use Jenkins for it. Today we will be discussing the work we did with Jenkins to meet the requirements of our service. First, uptime. Any service you work on, you want to make sure it's available as much as possible to your users. Typically these days, you implement your service as distributed ones across several data centers. If one or two data centers goes down, your service is still available. If there are parts of your service that are singletons, that is only one instance can be up at a time, you want to make sure you have quick, automated failover mechanisms in place for them. Our second requirement was security related. We wanted to make sure all master node communication is encrypted and secure, and without the use of SSH, which I will talk about. Finally, we want to make sure as we scale up, add more projects and nodes, our service continues to perform well. Usually with software like Jenkins and other tools and services, the way it works is you start using them, and as you go along and scale up and face issues, you then start tackling them. We went through a process where we did tests and work upfront to make sure that each of these requirements and others would be met for our service. And on top of making custom plugins and coming up with best practices, we spent a lot of effort looking under the hood, understanding what's going on in Jenkins, and that allowed us to make impactful changes which we could not have done if we just limited ourselves to writing plugins. And we will be sharing what we've learned with you. Hopefully, this talk is going to be informative, enjoyable, and most importantly, there's something you can take from this and apply to your Jenkins instances, especially big ones. Finally, I'll share some thoughts I have for future improvements and for Jenkins. So our first requirement is uptime. Jenkins is a singleton service. You can't have two active masters working on the same projects at the same time. And also, its configs are on local disk. There's no built-in, fully automated failover process. People are doing failovers in certain ways, which we will talk about. And on startup, Jenkins reads a lot of its configs. And a concern there could be, as you scale up, you keep adding more projects. How does that affect startup time? And that's important because startup time is part of failover time. So when coming up with requirements like this, it's good to have numbers in mind so you can measure against them. So we said, okay, let's say we have a Jenkins instance of 500 projects with 100 build history for each project. We should be able to do a failover with it in 2.5 minutes. So how do you do failovers with Jenkins? Well, typically that involves two things. Number one, backing up your Jenkins home directory. And number two, doing the actual failover from one master to another. So for backing up your Jenkins home directory, what some people do is use things like NFS and shared disk. You might have heard things like that in other talks today. What you do is you basically bring up a machine, attach an NFS mount to it, have the Jenkins home on the mount. If there's a problem with that machine, you bring up another one, attach the same mount, and you're good to go. If you're running your masters in different data centers across the world and in sort of the cloud way, you don't have access to these kind of utilities usually. Other people, what they do backups of their configs to a source control system like Git. These are usually partial backups. The Jenkins home directory is pretty big and usually only back up certain parts of it to a source control system. And it is automated though. Usually whether it's an external cron job or if it's a plugin that does regular backups, it is automated. Finally, the other thing people do is they do entire backups of the Jenkins home to a storage system like in the cloud. These are full and also automated. There are plugins out there that will do, for example, a full backup every 1 hour and incremental backups in between. As for doing the actual failover itself from one master to another, typically that involves starting up a new machine or VM, downloading the latest backup, and then starting up a new master. I don't have data on this, but I'm guessing most people do this manually. And we really want to do it automated in a certain way. So what are we really talking about? What are our requirements for failover? Well, the way we would like it to work is we should be allowed to provision 3 Jenkins Master VMs or jobs ahead of time in 3 different data centers. One of the jobs becomes active, downloads the latest backup, starts up the master. It'll run and create new backups. If that job or data center becomes unavailable, one of the other jobs should immediately take over, download the latest backup, and start up a master. I want to highlight the importance of being able to provision the jobs ahead of time. Say you only provision 1 Jenkins VM in your cloud, and that's your master. When it goes down, you then provision the replacement VM. The time it takes to provision the new VM and for everything to get ready is added into your failover times. So we really want to provision these ahead of time. We don't mind paying the cost for it up front. So we started work on this. For the backups, I mentioned there are good plugins out there. One of them is written by CloudBees. One of them was written by another team at Google, which we decided to use and wrote an extension for it. For the failover part, the way we approach this is we wrote something like a startup wrapper. And basically what it does is when it starts up, it uses master election technology to try to acquire a mastership lock. If it acquires the mastership lock, it blocks until it gets it. But once it acquires it, it'll download the latest backup and then start up a Jenkins master. Finally, we did some small work with regard to nodes to make sure that they fail over from one master to another gracefully, especially as you're moving to different data centers. So what does this look like? You provision your 3 Jenkins master jobs in 3 different data centers. The startup wrapper runs on all of them. One of them will acquire the mastership lock. It will then download the latest backup and then start up a Jenkins master. If that job or data center goes down, one of the other startup wrappers will acquire the lock, download the latest backup, and then start up Jenkins. So we worked on this and got it working. We have full automated failovers. We don't need to do any manual work. So we said, OK, now we can go ahead and start measuring how long do these failovers take. So we wrote a test suite that basically does 10 failovers in a row, measures timings, and then averages out the results. We wanted to be able to run these test suites with different configurations, Jenkins of different sizes. You could have a small Jenkins instance of only 10 projects, a larger one, and vary certain parameters and see what the differences are. So we wrote a script that creates backups of different configurations. For example, we could say, create me a Jenkins backup for 500 projects, 100 build history for each project, and the build log size for each build will be small, let's say less than 1 kilobyte. So we created various configurations and ran the test suites and looked at the results. One of the things that stands out is that build log size matters. Here are results of 3 different configurations. Each of them has 500 projects and 100 build history. The only difference is the build log size. On the left, the log sizes were small, around lesser than a kilobyte. In the middle, there were 70 kilobytes, and on the right, 700 kilobytes. Keep in mind, these are still pretty small log sizes. Most people would have megs of logs, tens of megs of logs, or hundreds of megs of logs. We did do some tests with larger values, and they took a really long time. So we sort of said, with just these 3 sizes, you get an idea of the trend. Let's just focus on that. The blue part of the bars represent how long it takes to download the latest backup and uncompress it. The red area represents how long Jenkins took to start up and fully read all of its config. So you can see that just increasing the build log size does increase how long Jenkins takes to start up, which is interesting. But most of the time is spent downloading the latest artifact and uncompressing it. If you think about it, that makes sense. The bigger your build logs are, and remember, build logs are stored in the Jenkins home directory, the larger your backups will be. And build logs are usually highly compressible, so the longer uncompression takes for them. So how do we try to reduce the time for these? Well, there are different approaches you can take. One idea is let's play with different compression algorithms. But you know what would really be awesome? If we could just reduce the amount of information in the Jenkins home directory. If we can reduce the config size and the backup sizes, that would really help. What if your nodes sent the build logs directly to an external storage service and not back to the master, and it was not stored in the Jenkins home directory? That made a lot of sense to us. So we worked on that. We have a custom builder plugin we use for our builds. We are updating it so that it sends the build logs directly to an external storage service. It only sends back a small piece of information to the master, which is like the ID or the link to view the logs. This can be displayed in the console output, or you can render it in the Jenkins UI on the left-hand side. You can create a new link instead of console output, and that'll point directly to this. I think this sort of feature should be added to the default builders as well. Think about a master that is handling 100 builds at the same time. 100 build logs are being streamed to the master, which it has to process, and then write all of that to disk at the same time. That's a lot of burden you're putting on one machine. And you will have scaling issues with that. Also, there are plugins that depend or kind of assume that the build logs are available on Jenkins Home right now, and they do some sort of processing. Those can be rewritten to process the logs from some other location. That should not be too difficult. Also, one small optimization we made is, whenever you create nodes in Jenkins, it creates configs for them and stores them in your Jenkins Home directory. And I think over time, there's some stats and metrics that are gathered for nodes as well. Jenkins supports this concept of ephemeral nodes, that is, temporary nodes that just come and go. It doesn't store anything permanent for them in the home directory, and this sort of fit our use case, so we made use of this. All our nodes are ephemeral, so that reduces the size of the backup by a certain amount even. So once we do this, and we guarantee that the build logs that are stored on the master are really, really small, you can see there's room to grow before we hit our 2.5 mark that we set for ourselves. Here are the results for 3 different configurations: 500 projects, 1,000 projects, 2,000 projects, each with 100 build history each. You can see the red area, which is how long Jenkins takes to start up, does increase, but much more gracefully. And the blue area also increases more gracefully as well. The blue area, which is how long it takes to download the latest backup and uncompress it, still takes most of the time. And like I said, we can play around with that further and see if there's different compression algorithms we can use. But the key point is, the more you leverage an external storage system instead of just stuffing everything possible in Jenkins Home, the better it is for your failover timings and for Jenkins. So to summarize, the work we did for this requirement, we implemented fully automated failovers. We used an existing backup plugin, which you can use as well. We implemented a startup wrapper that uses master election technology. Our wrapper and our implementation uses Google-specific technology, so it kind of doesn't make sense for us to share it with you. But someone else out there can use the same technique with Zookeeper or Netflix Curator and get the same thing working. This could potentially be implemented as a plugin instead of a wrapper using Jenkins milestones. I think it's just cleaner to keep it as a wrapper, though. And finally, we discussed how storing your build logs on an external storage service can really help your failover timings. Our next requirement was security related. We want to make sure all master node communication is encrypted. Jenkins has 2 main types of nodes, SSH-based and JNLP-based. SSH nodes are not an option for us. In that model, you store configuration information on the master. The master has to know about every node and know how to connect to each one of them. And the master initiates the initial reach out and connections to the nodes. We want to have a model where we can dial up and down nodes externally to Jenkins. The master doesn't know anything about them, and have them dial in for the connections. You can do that with JNLP and even leveraging plugins or utilities like the Swarm plugin. JNLP authentication happens over HTTP, HTTPS. Also, when the JNLP connection is made to the master and communication happens, it is unencrypted. So this is not going to work for us. When we were discussing this requirement, we said, okay, what do we do about this? How do we address this? One of the ideas we discussed was adding encryption support to JNLP. That seems like a valid suggestion. After much discussion, we actually decided the best thing for us to do would be to make sure all master node communication happens over encrypted RPC. This is another technology used at Google, which has been open sourced as gRPC for those interested. And the reason we did this is because we really trust RPC. It's a Google technology which we use a lot, so that's why we chose it. So what are we really saying? We're saying we're going to add a new node type. There's SSH nodes, JNLP nodes, and now we want to add a third one called RPC nodes. How do we do this? We had no idea if this was possible or how to go about doing this. So we spent a lot of time learning how network communication happens in Jenkins. Most of this logic is not in core. It's in a separate GitHub repository called remoting for those interested. So we basically spent a lot of time trying to figure out how do we add RPC support, not only to remoting necessarily, but we might have to modify core as well because the master does have to communicate to the nodes as well. And we were very scared we would have to rewrite a ton of code in Jenkins to make this happen. Not only in the remoting, but in core. And we'd basically diverged so much from upstream Jenkins, it would be bad. So to give you a very high-level overview of how network communication happens in Jenkins, what we learned, at least for JNLP nodes, on the server there's a TCP listener, which is basically a server socket. When the node starts up, it makes a socket connection. And over that initial connection, there's a handshake process that happens. If that's successful, it creates a Jenkins communication object, which is called a channel. And that's what's used for master node communication. And the channel uses the socket streams under the hood. So we realized we could do something very similar for RPC nodes. We can basically have an RPC server sitting on the master. The nodes can start up, make an RPC connection to the master. After the handshake is successful, the same channel object can be reused and created, but instead of using socket streams, it would use RPC streams. So the best part about this solution is we had to do no rewriting whatsoever. We just had to add classes that added RPC functionality to the remoting module. The RPC server we could implement as a plugin for the master, so we won't have to add any dependencies to RPC on core directly. All the dependencies would be pulled in through the plugin. So while we were working on this, we asked ourselves, could we improve the experience of managing nodes at large numbers? Usually in Jenkins, you manage nodes through the UI or the API. Plugins like the Swarm and the CLI actually do that. API interaction happens over HTTP, HTTPS, which is a no for us. Managing it through the UI at large numbers is kind of a burden, adding and removing entries. So can we make this better? So we realized we could do something similar to what people do with the Swarm plugin, which is, when, let's say, node 56, which is an RPC node, dials into the master, and it's authenticated, so the RPC authentication succeeds. Even if the master hasn't seen this node before and it doesn't have an entry for it, let's just create one on the fly. Just create node 56. So the experience will be node 56 dials in, the master says, yeah, you look valid. Oh, I don't have an entry for you. I'm just going to create one dynamically. You're good to go. And the cool thing is, and we made these ephemeral nodes. And like I said, the cool thing with ephemeral nodes is once you shut down the node machine, for example, and the node disconnects and goes away, the master auto-deletes that entry. There is no manual management you need to do for node entries now. They automatically add themselves when they connect and are successful, and they'll remove themselves when they go away. So fully automated node management, awesome. So to summarize, the way we met this requirement is we learned a lot about remoting in Jenkins and added RPC support. We implemented the RPC server as a plugin on the master, and we built dynamic ephemeral node registration as part of the handshake process. I should mention, this work has not been upstreamed yet. We use RPC at Jenkins at Google, and we need it for our work. We're not really sure if others would be interested in using this. If you are, let us know, and we could work on that. Our third requirement that we will discuss today was performance at scale. Can Jenkins scale to our future needs? How will it perform as we keep adding projects and nodes? One thing I want to mention is a lot of Jenkins users scaled nodes up using executors. What I mean by that is, let's say you need the capacity to do 100 simultaneous builds. One way, so instead of creating 100 nodes and having them run on like 100 cheap VMs or machines, what you tend to do is create 10 beefy nodes running on big VMs or big boxes and have 10 executors per node. The nature of our builds requires to really run one build per node. So scaling using executors is not an option for us. We really need to scale using nodes. Again, when dealing with requirements like this, it's good to come up with numbers that you can sort of measure for. So we said, okay, if there is a Jenkins instance with 500 nodes dialed in, we should be able to run 500 builds per minute for a sustained amount of time. If the builds are just sleep 5 builds, basically like every minute, we should have 500 of them cycling through the entire system. And this should keep going on. And I also want to mention, we want to do this with modest resources. If you attend talks and look at how other people handle large-scale Jenkins deployments, one of the things you may notice is the masters had gigs and gigs of RAM, lots of CPU, insane supercomputers type of deployments. Remember, the nodes are the ones that are doing the work. The master shouldn't really need resources. So if we came across instances where suddenly the master required more work or more resources, instead of just feeding it more resources, we made an effort to figure out, why is it asking for more resources, and let's see if we can address that. So what we wound up doing for this is basically writing load tests that would bring up a Jenkins instance with n projects, have n nodes dial in. The projects would basically have two configurations, build me every minute, and just run a sleep 5 on a node. And basically, we ran the load test, we would maybe come across issues, we debug, make a fix, rebuild Jenkins, and sort of iterate on this. And we went through a number of iterations. One of the first things we tried is bringing up a Jenkins master and having 100 nodes dial in, and it was a bad experience. The master didn't do well at all. So we said, okay, let's just start simple, start at the basics. Let's have 10 nodes dialing in. So our first test was 10 nodes dialing in. The Jenkins master was based off 1596.2 LTS. One thing I want to mention is that we had custom jars in the Jenkins master class path, in the beginning of the class path. We realized this was an important thing later on, but it's worth mentioning upfront. So we had these 10 nodes dial in, and we noticed a huge spike in CPU, much more than what the master was given. So instead of giving more resources to the master, we said, okay, let's look under the hood. Let's try to understand what's going on and why it's needing these resources. What we learned is, typically the way you start up a node, at least the JNLP ones, is there's this small slave.jar file that you start up, and it dials into the master. One of the first things that happens is that the master transfers over a bunch of jars that the node will need to function. And there's a way it determines which jars it needs, and it was picking up our custom jars in the class path along the way. And our jars were big. I mean, there were 300 megs worth of jars in the class path. So if you think about it, 10 nodes dialing in, that's like 3 gigs of data being sent across. Yeah, I can see that's causing stress on the master. So we said, okay, some people might be using Docker or VM images for their deployments. You could do that for your nodes as well. A simple Docker container or VM images on startup of the node, download the latest, the slave.jar from the master and start it up. One step further is to have the slave.jar already baked in to your image. So we took it the next step. We basically said, why don't we just install everything a node will ever need ahead of time in the image? So basically, nodes have a jar cache for the Jenkins jars. So we basically pre-initialized it ahead of time and put it in there. So they have everything they need. There shouldn't be anything to download anymore. Let's rerun the test. 10 nodes connecting, jar caches have been initialized. We still observed a noticeable spike in CPU. So I'd like to remind folks, this is still only 10 nodes. You could do some sort of thing where, okay, I'll bring up 10 at a time, then another 10. You can do that sort of technique. But keep in mind, when we're doing failovers and you have 500 nodes connected to your old master, and a new master comes up, and there are 500 nodes banging on the door at the same time, you can't do this 10, 10, 10 technique. So we really need this to work. Also, I want to mention, most users won't see this issue with such a small number like 10. The only reason we're seeing this is because we have these custom massive jars in the class path. Those of you who are doing something like that, yes, you will see this. But even those who aren't will see this issue, but at just a larger number. It won't be 10, maybe it'll be 100. I don't know exactly what number. We didn't test with generic installations. But be aware of this issue. So if you're running at large scale, this will apply to you. So we went under the hood again, saying, okay, what's going on? What's causing this CPU spike now? So what we found out, the node is dialing in, and even if it has everything it needs, the master would still check. And the way it does this, it runs a checksum computation of all the jars in its class path in some other places, and then compares it against the jars on the node. And the node ones are already calculated and sort of stored on the node, so it just does a comparison then. So if you think about it, and it does this for every node, it doesn't cache the results. So every node that dials in, it has to do 300 megs worth of checksum calculation, which is CPU intensive. And that's like 3 gigs worth of checksum calculation for 10 nodes. So we said, okay, why don't we just cache these values? Why do we need to recompute them every single time? So we patched Jenkins to do this checksum caching. So we rerun our test, 10 nodes connecting, node jar cache has been initialized, checksum caching has been enabled. Now the spike in CPU was much more acceptable. And it was a one-time cost. The magnitude of the spike would be the same regardless of whether there were 10 or 100 nodes connecting. It's a one-time computation that it has to do. Awesome. So now we have the ability to throw massive amounts of nodes at our master. So we said, okay, let's go back to our original plan of doing our load tests. Let's have a Jenkins instance with 300 projects, 300 nodes dialing in, and that's 300 builds per minute. And let's let this run for 1 hour. At the end of 1 hour, we expect 18,000 builds to have been completed. We ran the test and looked at the results. We were disappointed to see that only around 6,000 to 7,000 builds had completed, which is represented by the red bar. So Jenkins was not able to keep up. Also, during the 1 hour, the UI experience was terrible. It would be slow, hang, and lock up. It was basically unusable. And also, we noticed when a build was scheduled and put on the queue, even if there were nodes available, it wouldn't be assigned to a node for a very long time. It would just stay stuck on the build queue. Again, we looked under the hood and did debugging, trying to understand what's going on. Jenkins has a global queue it uses for builds. Many components that want to use it lock it, do work, and unlock it. And it turns out that this was proving to be a point of pain. Some components were misbehaving at scale. One component in particular that comes to mind is one that determines which node will get a build. So basically, when you schedule a build, it goes in the queue. This component comes along, locks the queue, looks at all your nodes, figures out which one do I give it, puts the build on one of the nodes, unlocks the queue. And it worked sort of okay at 10 nodes, and as you scale it up to 100 or more, it just performed terribly. So my team made a number of concurrency bug fixes, reduced bottlenecks, and fixed components like this. We rebuilt Jenkins, ran our load tests again. 300 projects, 300 nodes dialing in, 300 builds per minute. And we were happy to see now Jenkins kept up. At the end of the hour, we had 18,000 builds completed. Awesome. So now let's take it further. Let's do our load test for 6 hours. We'll run it against 100, 300, and 500 builds per minute. And what we want to see is that the build throughput remains the same for all of these configurations. That is the number of builds completed per hour per node. And we also want to measure pickup time. That is, once you schedule a build, how long does it remain on the build queue before a node actually gets assigned the work? So we ran the test for all these configurations, and we were really happy to see that Jenkins kept up, even at 500 builds per minute now. Equally importantly, the pickup time was low, less than 5 seconds. This is very important. If you're using a build service like Jenkins and you schedule a build, if it takes minutes for something to start working on it, it is very annoying. So this was really good to see. To summarize the work we did for this requirement, if you're running large number of nodes or doing custom jars in your class path, it really helps if you initialize your node jar caches ahead of time in your images or just beforehand. We added checksum caching to the master. This pull request is still pending, I believe, upstream, so hopefully it'll be merged in soon. And we made a bunch of queue locking fixes. I think most of them, if not all of them, have already been merged upstream. So you should be getting them. You should already have them, in fact. This was a while ago. As we continue to use Jenkins, we might run into other performance issues. Some of you may be already running into issues that we're not aware of. We will continue to investigate and make improvements as needed. One issue we did notice was when there were a large number, like in the hundreds of JNLP nodes connected to your master, and you just shut down a good number of them at the same time, the master went into like an awkward state. We didn't really debug this much because around that time we decided to switch using RPC nodes, and we didn't see this issue with RPC nodes. Some of our fixes might have already addressed this. If someone else is interested, they can verify. Also, we did mention one of the things we considered was, adding encryption support to JNLP. Even though we decided to implement RPC nodes and we're using that, for the rest of the community, this would be really nice to have. So on our own time, we went ahead and implemented this, and there is a pull request pending for it. We also want to continue to use and improve our test automation utilities. We've sort of let them gather dust for a while, but what we really want is weekly, or better yet, nightly, have these automations run, the load tests, measure against 500 builds per minute, and if there are regressions in Jenkins that make performance worse, we can catch them. This might be something useful for upstream as well. I don't know how many of you maintain your own Jenkins fork, so I'll talk quickly about our experience. We forked the core and remoting repositories. We have automated nightly merges from upstream, nightly merges. And for the core, we merge from the latest LTS tag. For remoting, we just merge from master head because it's not touched very often. We found that if you're careful with how you make local changes, serious merge conflicts are very rare, and they're usually quick to resolve. We build Jenkins off of our fork and use it for our service. We've been upstreaming relevant contributions and will continue to do so. Now I'm going to ask you to take a step back and let's consider Jenkins and the future. In my experience, a lot of the problems people have when using Jenkins are related around to its use of a local disk, the state of the world being in local memory, which also might contribute to load up issues. And also, even with all the fully automated master failovers, even if you're using a shared disk for all your masters like NFS, you cannot do failovers without noticeable downtime. And normal in-progress jobs that were happening during the failover would be lost. CloudBees provides a long-running builds project that you can use, which will survive failovers, but all other types will be lost. And again, in my experience, the way people try to address these issues, it's more like workarounds. First of all, just throw hardware. Jenkins needs more CPU, give it more CPU. Give it gigs and gigs of RAM. There are metrics out there you can see people having 96 gigabytes of RAM for their master. It's really scary stuff. And of course, all sorts of fancy disks available locally. The other thing they do is limiting data retention. That is, you can only keep a certain number of build history for each of your projects, and also saying your build log sizes can only be this big. There's a plugin out there that actually you can use to monitor active builds, and it monitors the build log size as logs are coming in. And if the threshold reaches a certain point, it'll kill your build and mark it as failed. There is a plugin out there, and people are using it seriously. I'm not trying to make fun. This is what people are doing to solve these issues. These are serious, serious things people are doing. We live in an age of very cheap storage, and it's only getting cheaper. There is no reason we should not keep build history forever, which a lot of internal Google builds that we work on, services, they do. And why we should limit build log sizes. There's no good reason we should be doing this. If you're doing this, there's something wrong with your service. Finally, people do sharding. CloudBees has very good utilities to help with this, especially if you're sharding on business groups. If you're forced to shard for scaling reasons, though, that can be a little painful, and just managing more masters is a little hard to manage, or it's extra work for you. So I think people sort of skirt around the real issue. The real issue, in my opinion, is that Jenkins is a singleton stack. The entire master is a singleton stack, and it's using local disk. We can keep making performance improvements, and we will, and CloudBees is as well. But there's a limit. Vertical scaling has easily reachable limits. We live in the cloud age. Think of all the services available these days. We have distributed, replicated, fast databases. The databases are much faster than they were even 10 years ago. New software you write is no longer single stacks. They are distributed where the individual pieces are stateless. Imagine Jenkins as a true distributed cloud service. When I talk to my team about this, and we discuss what it would take, the amount of work, and how we would go about doing this, one of the things I always hear my team say is, we'd have to rewrite so much, and we'd potentially have to rewrite a lot of the plugins even that sort of depend on local state being available. It's going to be a lot of work. This is like Jenkins 2.0 I'm talking about, and I think it's overdue. Imagine this. No more dealing with this local disk or single masters. It's going to be a much more pleasant experience for those of you who maintain it. So to recap, today we talked about a way of doing automated failovers. We are using a startup wrapper. A similar approach can be implemented by someone else using Zookeeper or Netflix Curator. We discussed how leveraging external storage, storing your build logs somewhere else besides Jenkins home can improve your failover timings. We went over a little bit of Jenkins remoting internals and how we added RPC support to it. If you're running at a pretty large scale where you have a lot of nodes, or you're putting custom stuff in your class path, initializing the node jar cache ahead of time will help you. We've added checksum supporting, which hopefully will be merged soon. And we've made a bunch of queue locking fixes. One of the other things you can take away from this talk is developing test automation upfront and making that part of your process to gather metrics and gain insight is really, really helpful. I'm so glad we did it. It wasn't planned, it just sort of happened because we needed it, and it's been such a great thing. So you should do that for your services as well. Hopefully, you found this informative, enjoyable, and most importantly, especially for those of you running large Jenkins instances, there's something you can take from this talk and apply for yourself. Try it out. Scale to hundreds of nodes. Instead of using those 10 expensive cloud VMs with 10 executors, use 100 cheap VMs. It might save you some money. Finally, I said this in the beginning, and I will say it again. On top of writing custom plugins and coming up with best practices, we worked really hard on looking under the hood, understanding what's going on in Jenkins. And that has allowed us to make impactful changes which we could not have done if we just wrote plugins. It was hard and worth it. It could not have been done without an amazing set of people. We have Sabuj and Alan, who are our VM experts. We use virtualization a lot, and Sabuj is even now helping us with plugins. John over here is our manager. This project exists because of him. It was his idea. All key decisions, issues, and requirements he helps with. And finally, Scott, David, and myself have been learning Jenkins a lot. Scott and David are amazing software engineers. I am so lucky they're on this team. Scott did a lot of the RPC work that we discussed, and David did the queue locking fixes and a bunch of other stuff. Both of them have written a lot of custom plugins as well. Amazing software engineers, amazing people. All of these people are here today. I know it's the end of our conference, which is a bummer, but if you meet them, take the opportunity to talk to them. It'll be worth your time. Finally, writing these changes has been hard. Reviewing them, I'm sure, has been equally hard. If you get pull requests that changes parts of your service that you haven't touched for a very long time, or are making scary performance changes, those are hard to review. So we appreciate everyone who's helped with that, especially Jesse, Kosuke, and Oleg. Thank you. We still have some pull requests that are pending, so please look at them when you get a chance. They've been pending for a while, annoyingly. And also, we might have some more coming your way. Having a conference like this where you can come share what you've learned and listen to others is invaluable. So I'm grateful to everyone who's helped make this possible.